In this video, we're going to finish up Chapter 4 and work some more examples. So far, we've talked about Newton's first law, the law of inertia. It says that if the net force acting on an object is zero, the object can either be at rest or it's moving in a straight line at a constant speed. We also talked about Newton's second law, and it says it tells us what happens if the net force is not zero. If the net force is not zero, then the net force is equal to the mass times the acceleration. Obviously, the larger the force, the greater that acceleration is going to be. The larger the mass involved, the smaller that acceleration is going to be. In section 4.4, we're going to clarify the difference between mass and weight. We know that mass is a measure of inertia. Weight is the force of gravity on an object. Now, we haven't studied gravity yet, and later we'll come back and we'll talk about this idea that every mass in the universe is attracted to every other mass in the universe, but this attraction is very, very small unless one of the masses is very, very large. In this case, the only mass large enough to produce a noticeable gravitational attraction is the mass of the Earth. And because of that, everything near the Earth accelerates with an acceleration of 9.8 meters per second squared. The weight in this case then is simply equal to mg, where g is the acceleration due to gravity. We know for on the Earth, g is 9.80. If we happen to be on the moon, g would be 1.62. But generally speaking, weight is equal to mass times acceleration due to gravity. They're definitely not the same thing. Mass is a scalar quantity. Mass is a measure of inertia. Your mass is the same every place in the universe. If you go to the moon, because the acceleration due to gravity is different, weight is going to be different. In fact, you weigh about 1/6. So for example, if we have an object, let's just write down, that's on Earth. Whoops. And I didn't put my units, but those are my units. And that's on the moon. What's that mean? Well, it means that if I have a mass of 10 kilograms, that the weight on the Earth is 10 kilograms times 9.80. And of course, it's measured in newtons because all forces are measured in newtons. Now, most of the time when we talk about weight, we talk about the magnitude of what something weighs. We don't usually talk about the fact that it's a force and that weight is directed down. So when you see something written like this, basically, I'm just saying that's the magnitude of weight. I know the direction of the weight when I'm solving problems is going to be a vector that points downward towards the center of the Earth. If I happen to be on the moon, though, that same 10 kilogram mass now has a weight of about 16 newtons. So when you go to the moon, your inertia doesn't change. In fact, for a horizontal problem, it would take just as much force to accelerate you because force is mass times acceleration. However, if you were trying to pick the object up, it would be much easier to lift it up because you won't have to overcome such a strong force of gravity. Very much the way if you pick somebody up in the swimming pool, they feel much lighter. That's maybe not a direct example, but it'll be a lot lighter. Let's do an example. Different example. That's a simple example. Suppose that we have a 1.96 times 10 to the 4th Newton luxury car. First thing you need to realize is since this is in newtons, we know this is a weight. It's not a mass because it's in newtons. It's not in kilograms. So 1.6, I think I left out my article. A 1.96 times 10 to the 4th Newton luxury car is traveling in the positive x direction when it makes a sudden stop. If the net force is negative 1.50 times 10 to the 4th newtons, what is the car's acceleration? We know the weight of the car, we know the force, we'd like to know acceleration. Newton's second law says that the net force is the mass times the acceleration. I don't know the mass, I know the weight. But one really great thing in physics is if I know mass, I know weight, because it's always a really easy conversion. So I know weight is mg. So 1.96 times, whoops, turn those around. 1.96 times 10 to the 4th is the mass times 9.80. Notice it's roughly 10. So if it weighs 1.96 times 10 to the 4th, its mass is around 1.96 times 10 to the 3rd. When I actually do the dividing, the mass comes out to be exactly 2,000 kilograms. I'm not going to worry about significant digits yet. I know I have 3 at the beginning in the problem. That's how many I'll keep at the end. So negative 1.50 times 10 to the 4th, that's the net force, equals 2,000 A. When I divide, I'm going to get negative 7.50 meters per second squared. If we want to, we can express that acceleration in terms of g's. There's a lot of places in the book where they'll talk about the acceleration as 5 g's or 2 g's. If you want to express it in terms of g's, you use the fact that you have negative 7.50 meters per second squared. And you know that 1 g is 9.80 meters per second squared. Again, the negative in this case is just that the acceleration is opposite the car's velocity. It was traveling in the positive x direction, so the velocity was positive, so the acceleration was negative. It slowed down to a stop. If I do negative 7.5 divided by 9.8, it comes out to be about negative 0.765 G's. So you can measure acceleration in a unit called a G, and 1 G is 9.80 meters per second squared. Let's look at an example, different example. Crane lifts a steel beam with a mass of 750 kilograms at a constant velocity. How much force does the crane exert on the beam? I don't know if you know what beams are, but they're big pieces of heavy equipment, and they have like a pulley on the end, and they're used to lift heavy things. They look something like this. So here's a big old I-beam. We don't usually draw art, but that's kind of a picture of the gist of things. Let's draw a free body diagram. Free body diagram looks like this. We know the weight is pulling down because we can't get rid of weight. And we know the crane is pulling up. And you could call this a couple of things. You could say it's an applied force by the crane, or you could call it a tension, because anytime you lift something with a cable, rope or cable or chain, that upward force that is called the tension. So either one of those labels works just as well as the other. The key to this question right here is this: constant velocity. Anytime something moves at a constant velocity, we know the net force is 0. So I know that the tension in the chain has to be equal to the weight. That's the only way the net force is 0. The other way I could say it is I could say something like, if I add up all the forces, T plus W has to equal 0. But now I have to be real careful that I put the weight in as a negative number. This would be a positive, this would be a negative. But I'm happy enough with this picture just to say, hey, you know, the tension has to equal the weight. So the tension has to equal 750 kilograms times 9.80 meters per second squared, because that's just mg. 750 times 9.8, and I get 7,350 newtons. As long as the tension in that crane is 7,350 newtons, the net force is 0, and it'll move at a constant velocity. Now, if I change that, what if I had to say, hey, let's do a slightly different problem. What if I tell you that the tension in the chain, I am going to write down this weight, we figured out it's 7,350 newtons. What if I tell you that the tension in the chain up is 7,500 newtons? Now we're not going to move at a constant velocity because now the net force is no longer 0. In this case, we know that the net force has to equal mass times acceleration, but that's going to be a positive 7,500 and a negative 7,350, and that equals 750A. Right there's that net force. That's 150. If I divide 150 by 750, I'm going to get 0.2. I still do have 3 significant digits, so I'll put those extra zeros. Meters per second squared. So now we actually will accelerate. The beam will be going faster as it moves up. Okay, hope everybody's comfortable with the difference between mass and weight. It's really W equals mg. If they give you something in newtons to describe weight, that'll be describing weight. A 20 newton, I don't know, book, whatever. If they give it to you in kilograms, they're definitely giving you mass. All right, Newton's third law. All right, the first thing that we really have to understand Newton's third law is that all forces are the result of an interaction between two objects. There's no such thing as an isolated force. All forces come in pairs. And these pairs are equal in magnitude and opposite in direction. If I want to describe it with the formula, I say that the force of A on B is equal but opposite, I can make these vectors, of the force of B on A. That's true 100% of the time. And it's one of the places where students sometimes get really confused. If I swing a golf club and the golf ball goes flying off, a lot of people think that the force on the golf ball must have been larger than the force on the golf club. But that's not true. The force that the club exerts on the ball is exactly equal to the force the ball exerts on the club. But remember, those are two different forces acting on two different objects. Whether or not the object accelerates depends only on the forces acting on it. The force that the ball exerts on the club has nothing to do with whether or not the golf ball will accelerate. Now, what does have a lot to do with whether or not something noticeably accelerates is size. What are the masses? Think of the interaction when an apple falls to the earth. Here's the earth, and here's the apple. If the apple is pulled down by the earth, that means the earth is pulled up by the apple with the exact same force. So if this apple weighs 1 Newton, that means earth pulls down on it with 1 Newton. It also means the apple pulls up on the earth with 1 Newton. That force is equal. If you weigh, and I don't know, weights are big numbers. If you weigh 500 newtons, roughly 50 kilograms, roughly 110 pounds, it sounds huge and it's not. If you weigh 500 newtons, That means the earth is pulling down on you with 500 newtons. It also means you are pulling up on the earth with 500 newtons. But if we think about that, if the force of A on B is equal to the opposite of the force of B on, that means the mass of the apple times the acceleration of the apple, that's the force of the apple on the apple, equals the mass of the earth times the acceleration of the earth. Now what you might realize is this number is huge. That means this number is going to be tiny. And that's if this was actually the net force. The truth of the matter is, to know whether or not the earth would accelerate, you'd have to know all of the forces acting on the earth. And chances are, if there's an apple falling to the earth in this hemisphere, somewhere on the opposite side of the country, there's a kumquat falling to the earth. And it doesn't, pulling it in the opposite direction. But what I really want you to realize is, the same force, these have the same force, can cause large accelerations when the mass is small. So if you have a small mass, you can get a really big acceleration. But if you have a really big mass, you can get a really small acceleration. So the golf ball is pretty small. It's got a pretty good force on it, so it noticeably goes flying off and accelerates. The club has other forces. You're holding the club. You're exerting a force that's different than the force of the ball on the club. Like I said, to know whether or not something accelerates, you don't look at what forces it exerts. You look at what forces are being exerted on it, and only the forces that are exerted on it. This law is true 100% of the time. If a tow truck pulls a car, then the force the tow truck exerts on the car is equal to the force the car exerts on the tow truck. If a horse is pulling a cart, the force the horse exerts on the cart is equal to the force the cart exerts on the horse. I know some people say, doesn't that cancel out? How do they go anywhere? They don't cancel out because they're not acting on the same object. They don't create a net force of 0 because they're not on the same object. If you want a net force on an object, you look only at the forces on that object. All right, let's do one more thing with this. Let's just think through. We've got a book on a table, and this book weighs roughly 10 newtons. Let's think about the forces that are acting on the book, and then let's think about the reaction forces. The forces on the book, and it's in equilibrium, it's just sitting there, are these two forces. The earth is pulling down, we call that the weight. And we have the normal force. That's the table pushing up. And we can see that if it's at rest, according to Newton's first law, those two forces are equal. So if it weighs 10 newtons down, the normal force is 10 newtons up. But those are not an interaction pair, which is what we call in Newton's third law. If you have two objects, you always get an interaction pair. You may have learned you have an action and a reaction. And that's okay, but the terms action, reaction make it sound like one force happens first and the other one happens second. But they happen simultaneously. It's an interaction between these two objects. They happen at the exact same time. This is not an interaction pair. This is the net force acting on the book. So this is F net, this is on the book, equals N minus W, which is 0. That applies that. Okay, what are the action-reaction forces? There are, or better phrase, the interaction. The interaction is that if the Earth pulls down on the book with 10 newtons, then the book pulls up on the Earth with 10 newtons. That's an interaction pair. Earth is pulling down on the book, that's the weight. That means the book is pulling up on the Earth with 10 newtons. Now, this is not part of a free body diagram because we're not interested in what's happening to the Earth. If I'm interested in what's happening to the Earth, I have to draw the Earth and draw every single force that's acting on the Earth, which would be really, really hard to do because there's a lot of forces acting on the Earth. So that's not part of this picture, but this is the interaction pair. There's another interaction pair involving the table in the book. If the table pushes up on the book with 10 newtons, then we know that the book pushes down on the table with 10 newtons. That's my interaction pair. This part's part of the free body diagram because that's the force exerted on the book. This is not part of the free body diagram because that's a force that the book's exerting. So the book's doing two things. It's pulling up on the Earth and it's pushing down on the table. But those aren't part, those are exerted by the book. When we draw a free body diagram, it's what's happening to the book. Well, the table's pushing up with 10 newtons and the Earth's pulling down with 10 newtons. So I hope that it really helps kind of clarify that these two forces that are acting on the same object are not an interaction pair. An interaction pair is always on two different objects. Apple on the Earth, Earth on the apple. Club on the golf ball on the club. You kick a soccer ball. Force of the kick on the soccer ball and the foot on the soccer ball on the foot. If I go over here and act like an idiot and try to punch this wall, you can't see the wall, but there's a wall, there'd be a force on the wall, and there'd be an equal force on my hands. So it's never a good idea to punch a wall. The harder you punch it, the harder you hurt your hand. All right, we talked a little bit about free body diagrams already, but I do kind of want to work a couple of examples for you and just look at some things. Look at the tension in a massless chain. Now, obviously, there's never really such a thing as a massless chain. And there's times where it's reasonable to assume that something's massless, a piece of fishing line. Probably for a chain, it's probably not that reasonable. But here's our situation. We have the ceiling. There's my ceiling up there. And here's my chain. And hanging from this chain, I have this 200 kilogram in the problem in the book, it was a sound reflector. It doesn't even matter what it is. I have this 200 kilogram mass. Okay. If I want to think about the tension in the chain, I can draw a free body diagram right here. Let's look at this point right here. I know that we're looking right at the end of the chain, that I have the weight pulling down, and I have the tension pulling up. Since there's no motion, this is an equilibrium problem. Everything's at rest. I know these two have to be equal, so I just need the weight. So I do 200 times 9.80. I get 1,960 newtons. I'm going to assume that I really do have 3 significant digits there, which means that the tension in the chain also has to be 1,960 newtons. That's really easy. And it doesn't really matter what point we look at. I can look at a point right here in the chain. I still have that same situation where this doesn't have any mass. So the only thing I have to worry about is, well, if the tension right here is 1,960 pulling up, then this tension right here also is 1,960. Or I could look at it right here. Same thing. I'd still get 1,960 if I have a massless chain. The tension would be the same everywhere in a massless chain. Now, what if I change it where the chain has a mass of 10 kilograms? So now I have a situation where the tension in the chain is not going to be the same everywhere. I'm going to call this point A, B, and C. If I start up at the top, let's start at point A. If I start at point A, nothing's different. I have the weight pulling down, and I have the tension in the chain pulling up. This is 1960. This is 1960. But if I go up to the ceiling, if I go back up to point C, if I draw a free body diagram for that point, that has a mass of 210 kilograms, and gravity is pulling down on 210 kilograms. If I do 210 kilograms times 9.80, I have to look here and see what I got. I get 2,058 newtons. Let's assume we only have 3 significant digits. 2,060 newtons. And this means this weight here is 2,060 newtons. Then the tension in the chain is 2,060 newtons. Notice I don't have the same tension anymore. The tension at the top has 100 newtons greater than the tension at the bottom. That makes sense. You would expect there to be more tension at the top because it's supporting more weight. If I pick a point in the middle, it's just a matter of assuming that the chain is a uniform density, and so half a chain is 5 kilograms. So if I pick point B, if this is point B, I now know that the weight being supported is 205 times 9.80. It's about, didn't do that right, 205 times 9.8. I get 2,010 newtons. So now the tension is 2,010 newtons, which is exactly halfway between the 1960 and the 2060. So it makes sense. The tension here, so if you're at the bottom of the chain, the tension's only 1960. Halfway it was 2010. Way at the top it's 2060. So when the chain had mass, we didn't get that uniform tension, the same tension everywhere that we get with a massless chain. We'll work a couple of more problems. One sort of classic fun problem is the example of weighing in an elevator. It brings up this idea of apparent weight. Apparent weight is a weight that you appear to be, but is not actually your true weight. It actually does not tell you the force of gravity acting on you. When we talk about things in orbit, we'll talk about the fact that the astronauts in the International Space Station appear to be weightless, but they actually weigh quite a bit and have almost like 90% of Earth's gravity is still acting on them in the space station. But we'll explain why they appear to be weightless. If you weigh in an elevator, picture this elevator. Now, one important aspect of elevators, this is not a Willy Wonka elevator, this is a real elevator, and they travel in a straight line, up and down. So, here's a cable. Inside here is a scale, and on that scale is a person. If you think about drawing a free body diagram, there's two forces acting on the person. Those two forces are the person's weight pulling down and the force of the scale, which is the normal force pushing up. The weight pushing down and the normal force pushing up. Now, if that scale is at rest, you know the net force is 0. So if the scale is at rest, the normal force, or the force on the scale, simply equals your true weight. Let's make up a weight. Suppose we have a 50-kilogram person. Now let's make it something different than 50. Let's have a 45-kilogram person. That's probably a child, so their weight, 45 times 9.80. So their true weight is 441 newtons. So if the elevator is at rest, the scale is going to read 441 newtons. Now, what if the elevator is not at rest? What if the elevator is moving at a constant velocity? Well, if it's moving at a constant velocity, and it doesn't matter whether it's moving up or down. If it's moving at a constant velocity, the net force is 0, which means the scale is going to read your weight, which is 441 newtons. So, if you're at rest, the scale gives you a true weight. If you're moving at a constant velocity, the scale gives you a true weight. Both of those are equilibrium conditions. It doesn't matter if it's static equilibrium or moving equilibrium. it reads the true weight. When it doesn't read your true weight is when you're accelerating. Let's consider that. Suppose that the elevator is accelerating upward at 2 meters per second squared. If you are accelerating upward at 2 meters per second squared, then you know the net force is up. It's positive. Look at the picture. Your weight does not change. But if you're accelerating upward, then you have a normal force that is got to be greater than your weight. That's the only way you'll accelerate upward, is if the normal force, they're telling you that it's accelerating upward, then you know that the normal force is bigger than your weight. And here I'm just talking about the size of the normal force. How much bigger? Well, the net force. The net force equals this minus this. The normal force is positive. This weight is negative. So you've got 45 kilograms times your acceleration. Remember, net force equals mass times acceleration equals the normal force, which is what the scale reads. Oh, I didn't put in the acceleration. Let's rewrite this. Mass times acceleration is net force. This is the one we're interested in. This is what the scale reads. If you prefer, we could write the force on the scale. So 45 times 2, force on the scale, minus 441. That's going to be 90. So the scale is going to actually read 90 plus 441, which is going to be 500, that's an S, 531 newtons. We call that an apparent weight. You appear to weigh 531 newtons. Picture that, close your eyes and think about it. If you're standing in an elevator and you're accelerating upward, you feel that floor pushing against you to push you up at a faster speed. You know you feel heavier because what you sense is weight, in a sense, is you pushing down against the surface. When it pushes up against you, you feel yourself pushing down harder. So you appear to weigh more. Now, doesn't matter whether the elevator is moving up and accelerating upward, in which case it'll be getting faster, or whether maybe it's headed towards the bottom and it's slowing down. If your velocity is down but your acceleration is up, you slow down. So either way, if the acceleration's up, you're going to weigh more. Apparently. You don't really weigh any more than 441. But that scale is going to read 531, and you're going to feel heavier. Now, what if it was accelerating downward? Let's let it accelerate downward. At negative 1.50 meters per second squared. In this case, if the net force is down, or you could say the net force is negative. The only way to accelerate downward, these are the two forces acting on you, is if your weight is bigger than the normal force. Your weight is going to be if your weight is bigger than what the scale reads. All right. Same formula. We know the net force equals the normal force minus the weight. So mass times acceleration. Your mass in this problem was 45. The acceleration is negative, and that's really important. I don't know what the scale reads. In fact, I was going to change that to scale. I don't know the scale reading, but I know that the person weighs 441. 45 times 1.5 is negative 67.5. When I add that 441 to the other side, I get 374 newtons. In this case, I appear to weigh less. Well, picture standing in an elevator and it accelerating downward. It feels as if the floor is dropping out from underneath you. In fact, if this elevator cable broke and snapped right there, you would feel weightless. Because what's the acceleration if it snaps? If it snaps, the acceleration is negative 9.80. That's free fall. If that elevator cable snaps, you'll be in free fall. The downward force here, the net force would be negative 441. Your actual weight is 441. The reading on the scale would be 0. That makes sense because how can it push against you if the scale and you are both accelerating down at the same rate? If everything's accelerating down at 9.80, you're going to feel weightless. You better hope that it never hits the bottom, but you're going to feel weightless. That's what's going on with astronauts. When they're in orbit, they're in free fall. And because they're in free fall, they feel weightless. Just like you, this person who's standing in this elevator when the cable snaps. He feels weightless. I want to take the time to do one more problem. It's kind of Newton's first law problem. It's really a vector addition problem, but I just think it's a good problem because I think I probably would put something very similar to this on the test. Okay, so you are standing at the corner waiting to cross the street, and you're walking your 2 Labradors. Here's you, and you've got Sam, and Sam is pulling with 125 newtons, oops, I wrote 35, so 135 newtons, and he's pulling at an angle of 30 degrees. This is due east. We'll just go with our, you also have Sam. Oh, did I already say Sam? This is Sam. This is Ellie. Ellie's a little smaller. Ellie's pulling with about 120 newtons, and she's pulling at about 40 degrees. And my question is, how hard do you have to pull on those? Which force do you have to exert? How hard do you have to pull to stand still so that no one accelerates, so that you don't accelerate? How hard and in what direction? equal to stand still. Anybody's ever tried to stand still while walking dogs, you know exactly what I mean. Well, the first thing we want to do is see how much force Sam and Ellie exert. I used to have a lab named Ellie, and my neighbor used to have a lab named Sam. They both passed away. I now have a lab named Luke, but I still use Sam and Ellie. Okay, so, and here's our coordinate system. This is north, this is west. There's our problem. The first thing we need to do is figure out how hard the dogs, what's the total force the dogs are exerting? Because what I have to do is balance that. I have to do the opposite. So, to get the resultant in the x direction, I would say 135 cosine 30 degrees plus 120 cosine, and here I have to be careful. I can use negative 40 or I can use positive 320. I'll use positive 320 degrees. I like to measure angles from the positive x-axis. I normally measure counterclockwise. I can measure clockwise, but then I have to remember that this would be negative 40. So I put that in a calculator. That's going to be a useful number. I'll tell you what, I'm going to write it up here. So 135 cosine 30 plus 120 cosine 320. Let me check my mode. I want to be sure I'm in degrees. I am. 135 cosine 30, 120 cosine 320. And my x component came out to be 208.84. I know I don't have that many significant digits. I'm going to pretend I have 3. I'm going to keep that one as significant. So we do the same thing. We get the y components. Fortunately, that's really easy because now I just have to change those cosines to sines. Again, I'm keeping that as a significant digit. That's what that little line over means. It's called a significance bar, a precision bar. It means it counts. So 135 sine 30 plus 120 sine 320. It came out really little. I'm not surprised that it's small. I might be a little bit surprised that this is a bigger downward force, but look at the angle. It's pulling downward. Even though Ellie's not quite as strong, she's pulling down towards the south a bit more. Okay. I gotta put those together. Pythagorean theorem. I should finish writing out my extra digits. 9, 6, 3, 5. I just want to have 4 just to have some extra. Okay, so I'm going to square that. Now I'm going to take the square root of everything. And it comes out to be 209. So there's my 3 significant digits. The total force is approximately 209 newtons, and that seems reasonable. It means they're both pulling with roughly 100 newtons to the east, and that seems plausible. All right. Angle y over x and then I have to stop and say, do I need to add 180 degrees? And the answer is no. If this x component's positive, I know I'm either first or fourth quadrant. I don't need to add anything. So I do second tangent, that's a tangent inverse, negative 9.635 over 208.84. I'm thinking that's going to be a really small angle down here in the fourth quadrant because I'm a little bit negative. It came out to be negative 2.6 degrees. I usually do angles to the whole number, but since this is such a small one, I'm going to keep it. Now, my question is, did I answer the question? How hard and in what direction do you pull to stand still? I know how hard to pull. I'm going to have to pull with 209 newtons. But I don't want to pull at negative 2.6 degrees, or else I'm pulling the same direction that the dogs are. The dogs are doing this. They're just barely negative with a force that's roughly 209. That's the combined effort of Sam and Ellie. I need to pull in the opposite direction. So I need to add 180 to that to get the right answer. So my answer is going to be 209 newtons, but I need to be pulling at about 177 degrees. And there I am going to round to the nearest whole number. Usually when I'm working problems and when you're working problems on the test, we'll round the degrees to the nearest whole number at the end. All right, I think that's all I want to say. We've covered pretty much everything in these videos so far for the first 4 chapters. See you in class. If you have any questions before class time, shoot me an email.